Okay, so good morning, everybody. Good afternoon for those that are in Europe. So today is the third lecture, and I would like to continue what I started, the program that I started yesterday. So discussing the universality classes for the different kinetically constrained models when one changes the constraint. So let me recall just what I was saying just at the very end of yesterday's lesson, which was a very simple geometric notion, but which is important for us recall. So first of all, let me recall that we are on Z2, so we are in 2 dimensions for the moment. So and might recall that each model is defined by an update family, which is a collection of sets, U1, U2, UM, which defines the rule, the constraint, meaning that in order to empty the origin, I need to have at least one of these sets. These sets are some set in Z2, which to be completely empty. And in order to empty another to update the configuration at the origin, I need that set to be empty. In order to update the configuration at another site, I need the translated one of the subset to this other site to be completely empty. Okay, so for example, let's keep in mind our one of our favorite examples. So the East model. We are in 2 dimensions. For the East model, the update sets are 2. U1 and U2. U1 contains the site to the right of the origin, and U2, sorry, and U2 contains the site above the origin. Okay. Okay. So now the notion that I wanted to recall is the notion of stable direction, stable and unstable direction. I pick a direction, this direction here on the plane, and I want to let you know if this direction is stable or not. And what I have to do to determine this is a simple thing. I pick a configuration which is completely empty. So let me put a big 0 here on the half plane perpendicular to the direction in the negative direction, and completely completely filled here, sorry, and completely empty here. Okay, and on this configuration, so it's a 2-dimensional configuration, I perform the, I run the bootstrap algorithm. The bootstrap algorithm empties in parallel all sites which have the constraint satisfied. And now for each direction, I will declare this direction to be stable, and I will usually indicate the stable direction with the red arrow. So this is stable. If when I apply the bootstrap algorithm, nothing happens, which means that all the sites which are 1 have not the constraint satisfied. Instead, I will say that the direction is unstable. If I can proceed further on, let this configuration evolve under the bootstrap dynamics, and so empty some of the occupied sites. For example, so here the case of the East model. So you can easily see that you can easily check that if I take a configuration which is here completely filled and here completely empty, sorry, so the other way around as yesterday. Sorry, one that is here completely filled and here completely empty. Oops. In this case, I'm considering this direction. This direction is a red one. It is stable. Why? Because all the sites which are occupied and that are here have the site above and to the right which are occupied. So the constraint is not satisfied. None of the 2 sites is empty. So this direction is stable. Same can be checked for the vertical direction, and also for any other direction. You can directly check that any other direction on the first quarter of the circle is stable. Instead, a direct check means can you make you see immediately that all the directions which belong to this other part of the plane are unstable, since that the corresponding half plane configuration can evolve. Okay, this is the notion of stable and unstable directions. Okay, so I can now go on, and I'm ready to define the different universality classes. So for the moment, it will be just telling you some, depending on the behavior of this stable and unstable direction, a classification of the different rules. But in a second, in 3 slides, you will see that this classification has is very relevant, because each of these classes corresponds to a different behavior. Okay, so the first thing that might happen, so which I will call the models that satisfies this property supercritical, is that if I look at all the direction of the plane, I discover that there is at least one open semicircle which contains only unstable direction, which means in my color code that I have at least one green semicircle. Okay, in this case, I see that the model is supercritical. It is the case for the East model, as you see here. This is the drawing for the East model. It is the case for the Fredrickson-Anderson 1F model, for which trivially, as soon as I have an empty site somewhere, I can continue to empty starting from that. In this case, there is not even one stable direction. And then we need a further division of this class in order to be able to capture the behavior of my models, because there will be 2 subclasses which display a different behavior. The models that I called rooted, they are those that they have a green semicircle, but they also have at least 2 stable directions, so 2 red directions, which are not perpendicular. So this case, in which I have 2 red directions which are perpendicular, still not in the rooted class. So the rooted class, its only cases. Sorry?
So Cristina, you mean non-opposite rather than not perpendicular for the stable directions?
No. It's all these. No, it's really non-opposite in the sense that I need to have, in order to be for a model to be rooted, I need to have at least. Now I don't see the red. Anyway, I need to have at least 2 red directions which are non-opposite. In the sense, if they are opposite, we will see in a second why this thing having just say E2, which is stable, and minus E2, which is stable, does not belong to the class that have a certain behavior, which is the class of all the models which have 2 non-opposite stable directions. In this case, there you have even 2 perpendicular ones, but it's not a perpendicularity which matters.
Yeah, thanks.
Okay, and then there is and then there is the second class, the unrooted models, which is everything else, meaning either models like FA1F, which do not contain stable directions.
Cristina, excuse me.
Yes.
There is a question in the chat.
Yes.
This seems very specific to 2D, correct? In 3D, are all supercritical models rooted?
Sorry, this is specific to? This is specific
2D,
to
2 dimensions.
To the 2 dimensions. Then, okay, there will be generalization to higher dimension are still, especially from this division is specific of the kinetically constrained models that not corresponds to something which is meaningful for the bootstrap dynamics. In general, for the bootstrap dynamics, they are a general classification is still up to come, even though it has been announced and it's going to repeat in the bootstrap community. Bella Bolbas, Rob Morris, Paul Smith, and I hope I'm not forgetting anybody, announced the result, universality results for higher dimensions. So they will have a classifications of supercritical, etc., giving the different behaviors for bootstrap. But in general, we don't have yet a classification for the stochastic model. So this is specific to 2 dimensions for the moment. Okay.
Thank you.
Okay, so so our root, as I said, is everything else. So either no stable direction, or just one or two, but opposite, as it is in this drawing. Okay. Okay. So now there is a different case. So the second class is the class of the models which do not contain a green semicircle. So if I look at any semicircle, I discover that there is at least one stable direction. But nevertheless, they have at least one semicircle which contains only a finite number of stable directions. This is the case for the FA to F model, which, as we will see in a second, sorry for is for the FA to F model, which has just 4 stable directions, which are the coordinate directions. We will see in a moment some drawings. And it is also the case for the Duarte model. For the Duarte model, there is the semicircle of the left semicircle, which is completely stable, all directions are stable. And in the right semicircle, the only direction which is stable is E1. So there is a semicircle which contains only a finite number of stable directions, also in this case. And also for this class, in order to capture the correct the behavior, to distinguish the different behaviors for the stochastic models, we have to distinguish to have a final classification, and to distinguish models such as FA to F, which have only a finite number of stable directions, which means that there are no completely red sectors like here, which means that there is an infinity of stable directions. Instead, there is an infinity of stable direction. The model, we call them infinitely critical. So finitely critical and infinitely critical corresponds to having a finite number or an infinite number of red directions. Last case is the case of everything else. Everything else meaning every rule such that for any semicircle, which I can pick up on the plane, this semicircle contains an infinity of stable directions. So there is, in any semicircle which I can look at, there is a red sector, so an infinity of stable directions. And this is the case, for example, for the northeast model. Remember the model in which that the constraint is requiring both the neighbor to the north and to the east, to the north and to the right, to be empty simultaneously in order to be able to empty. In this case, you can directly check there is only 1/4 of the circle which is of unstable directions, of green directions, and so it belongs to this class. So now so you had the patience to hear all this classification, and now some rewarding. So why these classifications are useful? Because they really distinguish among different behaviors. So first of all, I like to recall what happens for the scale, the scaling of time scales for the deterministic bootstrap algorithm with according to the different choices of the rule. And what happens is that there are 3 possible behaviors in 2 dimensions. For all the models which are subcritical, so to the class to which the northeast model belongs, so for all the models which do not have, for each semicircle, here you will always find a red sector, so an infinity of stable direction. In this case, the model have a positive critical density, which means that there is a critical density larger than 0, below which blocked cluster backbone, which are blocked under the bootstrap, percolate. So this critical density is the critical density of bootstrap percolation, so the one at which backbones percolate. Okay. Then I go in. Now I start from the first class that I defined, the one of models which have at least one semicircle which is completely green, completely unstable. In this case, the time scale for the bootstrap dynamics scales as an inverse power of the density of empty sites. And finally, the critical case. This is the case in which we do have at least one semicircle which is completely unstable, with the exception of a finite number of stable direction. Okay. In this case, and it is the case, for example, for the FA2F model, the scaling of the time scales for the bootstrap dynamics is exponential of possibly log correction divided by the density of empty sites to a power alpha, where alpha is a power which depends on the dynamics on the choice of the rules. For example, for the FA1F model, alpha is equal to 1. And it has also a geometric meaning. It's something which can be quantified. And what is this alpha? Alpha is what is called the difficulty of the model. What is the difficulty? The difficulty is for a critical model. See, I said that I have green semicircles, but they contain a finite number of stable direction. Each of these stable direction is a direction such that if I take the half filled and half empty configuration, I cannot empty anything with the bootstrap dynamics. But if I add some additional empty sites, I might start to be able to empty. And this alpha is a minimum over all the possible choices of the semicircle, with a maximum of all the possible stable directions on that semicircle, of this minimal number of empty sites which are needed to make the direction unstable, to make the bootstrap proceed. I think I have immediately, if it's not immediately, it's just after an example. Yes, it's immediately. So it's the example of FA1F. For FA2F, sorry. So for FA2F, you see that all the 4 coordinate directions are stable. For example, see here E1, the direction E1 is stable because all the sites that are here cannot be emptied. Each of these sites has at least 3 occupied neighbors, so the constraint is not satisfied. Same for the other coordinate direction. But the point is that notice that it is enough that I add one additional empty site here. So to this figure, I add now one additional empty site. And then starting from the neighbors of these empty sites, starting from here, I can start to empty because now the constraint is satisfied. I have 2 empty neighbors. Now I can move here, I can empty, and so on and so forth, also below. So I can continue the bootstrap procedure. If I have at least one empty site, I can unstabilize the direction. If I have at least one empty site in the next row. So this is the difficulty of the direction E1 for the FA2F model. The same by symmetry is for the other direction. So in the case of the FA2F model, the difficulty of the model, if I take the minimax over all semicircle, is simply 1. Okay, and that's in fact, if you recall from previous slide, I said that in this case, the scaling will be modulo log corrections exponential q to the power alpha, with alpha this difficulty. And in this case, for the FA2F model, this alpha is equal to 1. Is this this number of additional zeros that I have to add in order to be able to move. Okay, so.
Can I ask a question?
Yes.
Yes, Cristina, I was wondering, so this seems to mean that there is no model, no critical model with a real alpha.
Yes, the alpha are integer. It corresponds to, no, yes, in 2 dimensions, this alpha should be integers because there is this.
But you think you can hook up some model, critical models with alpha non-integer? I mean, does it make sense? Or
no, I don't think so. No, because if you mix up the rules, so if you want to have a non-integer alpha here in the exponent, but if you mix up the rule, if you The idea is perhaps to mix several rules, some rules that have a certain difficulty and the other with another difficulty. Then what dominates is just it's always the semicircle with the least difficulty, and then it's simply an integer number. Because for each direction is, I think it doesn't make sense in this framework.
Okay, thanks.
What happens for so this was just the results for the boots. So we saw the scaling for the time scales of the bootstrap dynamics. Now what happens for our kinetically constrained model? So for this stochastic version, which does not feature only emptying sites, but also filling sites. And as I anticipated, the answer is that in order to capture the behavior of these models, one has to refine the universality classes of the bootstrap. So in particular, among the supercritical rules, which all give rise to a inverse power law behavior for the bootstrap infection time, there are two distinct classes: those of unrooted models. Unrooted models were those that did not have two non-opposite stable directions. And for these models, also the scaling for the stochastic dynamics is an inverse power of the density of empty sites, though the power is different from the one of the bootstrap. And for the rooted models instead, those models like East, which contain at least two directions which are non-opposite and that are stable, the scaling is the divergence when Q goes to 0 of the time scales is much faster. It scales as 1 over Q to the power log Q, okay, as we saw for the East model. We saw it specifically in one dimension. And for the critical models, again, in order to capture the behavior, one has to distinguish among the two cases of finitely critical with a finite number of stable directions and infinitely critical with an infinite number of stable directions. And for the finitely critical model, what happens is that the time scale for the stochastic dynamics, so this mean over the stationary process of the infection time for the stochastic dynamics, scales as the one for the bootstrap percolation, where when I say scales as the one for bootstrap percolation, I mean that is an exponential of possibly log corrections and constant divided by an exponent alpha, where alpha is again the same as for bootstrap percolation, the difficulty of the model. But these constants and these log corrections that are above are in general different from the one of the bootstrap, or perhaps even always. And for the infinitely critical model instead, which contain the Duarte model, the scaling for the stochastic dynamics is much faster, as was the case when comparing for the supercritical rooted models, the stochastic dynamics with the deterministic dynamics. In this case, you see here, there is again an exponential form, but the power which appears in the density of empty sites, in the inverse density of empty sites, is not anymore the difficulty, but it's twice the difficulty. Okay, and we will see immediately why, where this 2 comes from. Okay. And I also wanted to mention that I reported here the results without the log correction, but there is a further finer classification of the models which allow also to capture for all the classes the log correction, which was done by Weiler, Tastke, and Laure Maraichet. Okay, so and I should also, okay, but it is the bibliography. It's just intended to be a mini course and not a seminar, but I want to acknowledge specifically the all my collaborators for this series of results, which are Fabio Martinelli, Rob Morris, Laure, and Ivailo. So these results for the KCM were obtained in a sequence of works. Okay, so now why this behavior? So okay, it's very nice that I can give you a classification, so that if you give me a rule, I can tell you which is the behavior, in which class is the behavior, but you are now probably want to know whether it's simple or not to understand why. Okay. So what is the mechanism behind all this scaling? So this is the mechanism. For the supercritical models, which are unrooted, which are those, I recall you, that have a completely green semicircle. And furthermore, they have one such semicircle such that also the opposite semicircle is green, because these unrooted models have at most two opposite stable directions. So they can have two directions like that. But I can always identify for this model two semicircles which are opposite and which are green. So for this model, it's possible to show that, so the mechanism is the following. It's possible to find a sufficiently large region, this region that I'm depicting here, such that, which I will call a droplet, such that if this region is empty, okay, if this blue region here is empty, I'm able to move it back and forth along the direction which bisects these two semicircles, which is this one here. Oh, sorry, it should not be red, otherwise it's confusing. So along this, I can move back and forth this droplet along these directions, these two the direction which divide in half this semicircle. So, and the point is that when I say I can move back and forth, what do I mean? I mean that by respecting the constraint of my dynamics, I can construct a legal path. So remember, for the first day, I defined the legal path, which are paths along the configuration in which all the possible moves are allowed by the dynamics, which allows me to pick this empty droplet and to construct a new empty droplet of the same form here, and then fill this initial empty droplet, so that the net result is that I have moved this droplet of one step to the right. Same on the left. Okay. So the key ingredient is the fact that, which is an ingredient that comes from the bootstrap percolation result, is that whenever I have a green semicircle, if I have a green semicircle, I'm able, if I only know that I have a green semicircle, I know that I'm able to construct a droplet, which can be, if empty, can be moved here. The sense that I can construct a path which empty this guy and empty this guy and empty this guy, etc. This is the only thing that I know when I have one green semicircle. When I have two, which are opposite, since the constraint do not depend on, so the dynamics is reversible, I can reverse the path, and the constraint do not depend on the to be updated side. So I can, if I can empty something in front of me, I can also refill it. So using the fact that from this, in the case I have two opposite green semicircle, since I can, from this black blue region, I can empty one blue region here, it means that I can also refill it thanks to this initial droplet. So in this case, what happens is that essentially you might notice that this dynamics is very reminiscent of what we saw yesterday for the heuristic of the Friedrichsen-Andersen one facilitated model. The case in which essentially I have single empty sites which move as random walks because they can move to the right and to the left. The only thing that I have to wait is the time to create one additional empty site for the F1F, which gave a scaling which is inverse of power law of the empty sites. This for F1F. In this case, what plays the role of the density of empty sites is an effective density, which is the density, the probability of finding an empty droplet. So these empty droplets have some fixed regions. If I want them to be empty, the probability to finding them empty is some power of Q. So the time scales, say the relaxation time or the infection time, scales as an inverse power of Q for these models. Okay. So now this is the case in which I can move this droplet back and forth. But what happens if instead I'm rooted? Rooted means that I have just one green semicircle, but the opposite one, this one, will necessarily contain at least two non-opposite red directions, which means that if I construct my blue, I can always construct a big region, a big droplet, this blue region, which can move in this direction. So in the middle of the unstable semicircle, but it cannot move back. In particular, okay, starting from this empty region, I can always construct a path which empties these guys and then empties these guys, etc., etc. Okay, which also explains why for the bootstrap percolation, these rooted models do not behave differently from the unrooted ones, because in order, if I'm sitting at the origin, which is here, and I want to know how long I have to wait in order to be emptied, I simply have to wait that from the nearest droplet, I can reach the origin. So this is simply an inverse power of Q. But instead, for these models, which have in which for the stochastic models, in which when I want to empty, I have to pay a cost to wait the time of being able to cross the energy barrier to empty that site. This path in which, if I'm sitting at the origin, I wait that everybody is emptied starting from the nearest droplet is super unlikely. And this is very reminiscent of instead should ring a bell towards what we saw yesterday as the heuristic of for the dynamics of the East model. So the East model does exactly like that in one dimension even. So I have an empty site, and starting from that empty site, okay, in the other direction, I'm able to empty the site on my left, and then and so on and so forth. But that's certainly not the smarter technique if I want, starting from an empty site, to reach another site which was filled to hit the origin, which is sitting here. But we also saw that the smarter technique requires anyway to go through a barrier, to an energy barrier, so to creating a certain number of empty sites, where the number of empty sites that I have to create is proportional to the logarithm of the distance of the site that I want to hit. And for these rooted models in 2 dimensions, the behavior is pretty similar in the sense that it's not at all one-dimensional, but there is a sort of constrained motion. Essentially, this droplet is also only able to move inside a cone, and which is the green cone identified by taking the perpendiculars to the 2 red directions here. And so the green cone, which is identified by taking these 2 perpendiculars. Inside that, my droplet is able to move. It's able to move because it's always possible when I want to move the droplet. See, if I want to move in all this direction, I always see around a semicircle which is green. If I start to want to move in another direction, I'm inside a semicircle which contains a stable direction, and it's not possible to find whatever big region you are looking at. This won't be able, if it is empty, to empty an equal empty region on along that direction, the next empty region, the next region. The point is that if I have some stable direction, they are going to let me lose something. When I want to move, I start from some droplet which is empty. If I have a direction in the semicircle inside this, if I'm moving along, say, this direction here, I want to move along this direction here, my droplet. When I move in that direction, the semicircle which is around that direction, I mean, to which this is the bisectrix, contains a stable direction, which means that no matter how big you choose your initial empty region, you won't be able to produce another region of the same form and the same size just after that. You will be able to empty something, but it will be eroded, say, with some parts missing. And so you won't be able to go very far. Okay, so using this fact, so the fact that for these models, due to the presence of these at least two non-opposite red directions, the motion of the droplet occurs just in a cone. It follows again that if I want to, from a single droplet somewhere, to create an empty site which is at a distance n far apart, I will have again to see a logarithmic number of empty sites, logarithmic in the distance from the droplet to this site that I want to empty. And this is this result is a combinatorial, again, as for this model, a combinatorial result, which is much more subtle to obtain. So for the East model, I told you yesterday that it's a very nice and easy argument to attain this logarithmic barrier. I will put it at the end of the slides tomorrow so that you can check it or on the bibliography. Instead, the result that there are logarithmic energy barrier for this model is much more, since we cannot use in general the orientation of the rule. So the rule of the East model look just in one direction. So they just look in these two directions. And this orientation of the rule, so in one dimension, in particular, just on the right, this orientation of the rule was a key ingredient, as you will see in the combinatorial argument that I will add for you to check after the course, if you want. If you want to understand these results, one has to go to a much more subtle combinatorial argument that was done by Laura Maréchal. But anyway, from the point of view of the heuristics of the dynamics of the model, the behavior, you should think of these rooted models as performing an East dynamics. So a dynamics which is has to cross, in which in order to move these droplets, these entities that can be moved in one direction, you have to cross logarithmic energy barrier. Hence, you will have a time scales, which scales as the inverse. So this is if it's a time, there is a minus here, sorry. Time scales as the inverse density of these droplets, and these droplets are simply large but finite regions, so which have a density which scales as a power of q, to the logarithm of the typical distance that I have to cover from the origin up to the first droplet. So a log of this same effective density, which explains the log square here as for the East. Let me explain now what happens for outside the supercritical class. So outside the class in which I have this finite empty region which are able to move at least in one direction. So now I'm moving to the critical class. So to the case in which for each semicircle that you can choose in your plane, you will find at least one stable direction. Okay, so it's not possible, as I said just before, to create a finite droplet that can move. But look what happens. Let's look to a specific example, to the Duarte model, to understand what happens in this case. The Duarte model is the case in which I have the constraint asks for an empty site, either at least two empty sites to be found in these three neighbors: the neighbor above, below, and to the left of the given site that wants to be updated. So see that in this case, I drew them before, but I will redraw them here. So in this case, the stable and unstable direction for this model are the following. So E1 is a stable direction, and all these direction in the positive direction are are unstable, and this part and to the left, all direction are stable. And also, if we now focus on the direction E1 here, so which is the minimal number of empty sites that I have to add in order to unstabilize this the horizontal direction. So let me take here on my drawing, I'm taking the configuration which is completely empty on the here on the left, starting from this column, and on the right, if this configuration, if here I had a completely filled configuration, nothing would be able to move. So the direction is stable. But as for the FA2F model, it is enough to put a single empty site to be able to unblock that direction. In fact, from this single empty site, I can now empty this site below, above it, because it has two nearest neighbors which are empty in this neighborhood, left, below, and above, and so on and so forth. So I can empty the whole column. And if in the next column to the right, I find at least one empty site somewhere, the same way, starting from its nearest neighbor, I can empty all this column, which means that if I have a column which is completely empty and which sees on the right at least one empty site on the next column, I'm able to move it to the right. Notice also that, so which corresponds to the fact that the difficulty of this direction E1 is just 1. I need just to empty one site. Notice also that this column of empty site is not at all mobile in the left direction. So if I have this column of empty site, no matter how many empty sites I add here, I'm not able to empty any other site, because the neighbor here doesn't look to the right. So this guy here cannot be emptied, cannot use the help of the empty column. So the moral here is that if I have an empty segment, which is sufficiently long, so 1 over q times log 1 over q, typically I will be able, since typically we see to the right on the next column an empty site, typically I will be able to move this empty column to the right, but never to its left. So you see that this means that this empty column of this length is a droplet which is mobile in a typical environment, in an environment in which I found an empty site on this long interval. But it is mobile with an yeast-like dynamics, a dynamics in which I can move only in one direction. And since the density and the density of these droplets, so the probability to see this empty column, which is mobile to the right, is we scale as exponential minus 1 over q, okay, which is the probability times log correction to find that empty column. But then, so it's immediate to see why the two results, why for the, so if I'm just looking at the bootstrap dynamics, then I simply, if I'm sitting at the origin, wait that sequentially starting from the next droplet, I reach the origin. So the time of the bootstrap will just scale as the distance from the origin to the next column of length 1 over q log q, which is empty. Hence the scaling for the time of the bootstrap. Instead, if I'm considering the stochastic dynamics, since this column can just move in one direction, in order to move, it will have to pay, as for the yeast dynamics, the creation of a logarithmic number of empty columns, where logarithmic is logarithmic in what? In the distance from the origin to the nearest empty column. Okay, I'm sitting here at the origin. I wait that this empty column arrives there. This empty column can just move in an yeast-like way, in an oriented way. So in order to overcome this distance, I'll necessarily, even though I can use the fact that I can create empty sites and then also fill them, so in order not to create all the empty sites up to reaching this guy, the best that I can do is to go through a configuration which sees log L empty columns. So I will have to wait a time which is inverse of the probability of seeing one empty column on the, according to the product measure, to the equilibrium measure, to the power log of this distance, which is again an inverse of this density. Hence, that's where the power 2 comes from. Okay, so I have the 1 over the effective density to the power log q, which gives the other q in the exponent. So if we do it as tomorrow, as yesterday, sorry, we should stop 5 minutes. Okay, so this is the behavior of the Duarte model, but this you might as behavior essentially in general for the models which have an infinite number of stable directions and that are critical. But I'll tell you a little bit later on in which sense. So in general, this this model will feature large droplets, large in the sense that they are diverging in when q goes to 0 as a power law, and that are going to move in an east-like way, this infinitely critical model. What happens instead for finitely critical models, those that have at least one semicircle with in which there is only a finite number of stable directions. So, for example, for this model for which I'm making here the rules, the behavior is the following. So you can readily check that the only stable direction are, as for FA2F model, the 4 coordinate directions. And I chose these funny rules because these rules are such that if you instead are a little bit asymmetric, so the difficulty of the 4 stable direction is not the same for all the stable directions. So there is one direction, which is this one, so the E1, which has just difficulty 1. And the other 3 stable direction have difficulty 2. You can, we are not going to check it together, but it's very easy to check it if you make this half filled and half empty configuration, that to move in the direction E1, since we'll just need to add one empty site, which corresponds to the fact that there is this one here and this one in the just one site in these 2 rules, we are able to move to the right, okay, but not to the left. If we want to move to the left, since the rules which have the empty sites on the opposite than to the left, so to the right, have 2 empty sites here required. The difficulty to move in this other direction is 2, and the same for the 2 horizontal, the 2 vertical directions. Okay, so this model is a little bit asymmetric, and it belongs to the class of what I call finitely critical model, for which I claim that the scaling is the same, in the sense with the same critical exponent as for the bootstrap dynamics. So what happens for this model? So one could think that, so the first guess could be, okay, so again, if I take, let me draw, again, if I take a column which is completely empty, and if I have an empty site, one single empty site here, this column is able to move to the right. But if I want to move now to the left, I will need to find 2 empty sites. Okay, so I could think that either I have to take a droplet that is of length 1 over q log q, which is just able to move in an oriented way, so in an east-like way, which will feature also logarithmic energy barriers, or I will have to take a longer droplet, say of length 1 over q squared, log 1 over q, so to be able to find the 2 empty sites. In that case, I can move back and forth. In that case, the motion will be FA1F-like, meaning that I can move back and forth. But in both cases, if this is the if this is the mechanism, I will get for the infection time a scaling which is exponential of order exponential 1 over q log q, because the density of these droplets, which are of this length, is the inverse of this one. And because if I want to move instead with smaller droplets, I will move east-like, and so I will feature an logarithmic energy barrier, which brings the second q in the exponent. So what happens? Why did I claim that it's again the scaling is instead the same as the bootstrap, and same as the bootstrap is for this model tau bootstrap is exponential. Let me not put the log corrections. C over Q, because the difficulty of this model, if I take the mini maximum over all semicircle, I find this semicircle, which has just open semicircle, sorry, it was open semicircle in my definition, which has just maximal difficulty over the semicircle, which is 1. It's the open semicircle, so I'm not taking the extremes. So, okay, so which is the behavior? So, so the reason why the scaling doesn't of the stochastic dynamics doesn't gain these 2 in the exponent at variance with the models in which I have which are infinitely critical, so that they have an infinite number of stable direction, is that the motion of these droplets occur in a very subtle way. So these droplets will be droplets which have the size, I think I didn't write them, but the size of the entities that move of the droplets will be 1 over q log 1 over q, okay? So that their effective density is exponential minus 1 over q. And these droplets now, okay, are free to move on the right, as we know, because the difficulty in that direction is 1. So typically they will find the one single empty site, which enables them to move to the right. Okay, so that we already know. But the mechanism is the following. One thing that the process will do is to move these, if once, say, we want to move in another direction, say in the vertical direction, this droplet of this site cannot move immediately in the vertical direction, because typically, if I am on the site 1 over q log 1 over q, I draw a square here, it's not the column, I won't find the 2 empty sites which are needed to move in the vertical direction. But what I can do is to move with my droplet to the right in an east-like way until finding 2 empty sites, and then take these 2 empty sites, and by reversibility move back my droplet, going to the same logarithmic energy barrier. And now I have these 2 empty sites which allow me to move in the vertical direction. So the moral is that to move 1 step in the vertical direction, I cannot do it immediately with a droplet which is so small with respect to 1 over q square, which is the typical size I will have to look at in order to find the 2 empty sites which are needed to go up to satisfy the constraint. But I can do that by previously making an excursion to the right on a distance which is order 1 over q square. And this excursion will be made in an east-like way, okay? So the moral is that my dynamics is able to do via allowed paths that are allowed in typical environments, so in environments which are typical with respect to the equilibrium measure, a motion which is of vertical in both directions. Actually, both the vertical direction up and down require just 2 empty sites in order to be unstabilized. I can do this by paying just the cost, meaning just waiting the typical time that I have to wait to move the droplet east-like to along this distance. So then what does it mean? How much do I have to wait? We saw that the time I have to wait for the east-like dynamics is the time to create a logarithmic number of this droplet, because any east path, any path which use only the oriented rule in this direction, will have to go through a configuration which has a logarithmic number of droplets. So the time that I have to wait is the inverse density of this droplet, which is, so this exponential 1 over q, to a logarithmic of this distance. But notice that this distance is order 1 over q squared. So the log of this distance is not the log of the distance to the next droplet. It's just the log of the distance to the next couple of empty sites. So this is a finite region. So is not going to look to the next droplet. And so the log of this distance just bring another additional log correction. So essentially, you have to think of finitely critical models as models in which the motion is very a sort of a hierarchical combination of east paths on mesoscopic distances. Mesoscopic in the sense that they are much more smaller than the distances among two droplets. So not the exponential 1 over q to a certain power, but they are order 1 over q to a power, so just inverse power of the density. So the typical distance to find some finite cluster, which is able to unblock the rule in the other direction. Okay, so in general, the behavior is this. So when you have a critical models, for all the critical models, the droplets, the entities that dominate the relaxation are some empty region which have a model dependent shape. Of course, you don't have to think about droplets as being rigid square shapes. The optimal droplets, those that will dominate the motion, will have some much more complicated shape, but their typical size is order 1 over q to the alpha, where alpha is this minimal number of empty sites which is needed to unblock one semicircle completely. And accordingly, they have a density q to the power of this size. Then the two behavior for infinitely critical and finitely critical is, in one case, these droplets can only move east-like, because there are some direction which in the opposite semicircle which have an infinite difficulty, because they belong to a when a direction belongs to, when there are infinite number of stable directions, the point is that all the directions that belong to a red sector cannot be unblocked by just adding a finite number of 0. It is the case for the directions to the left of the Duarte model. We saw that no matter how many zeros I was adding to the left, the presence of an empty half region to the right was not helping me. So this alpha would be infinite for these models if I was trying to go and look for the cluster of empty sites that are needed to unblock the other direction. So in this case, I don't have any other choices, better choice than moving east-like. So this is why I gain this factor 2 from the log of the distance. Instead, for the finitely critical model, there is this funny mechanism which involves on the mesoscopic scale. So on the scales needed to go to pick the clusters which can unblock the directions is east-like. And on the macroscopic scale, if I want to cover the scale which separates two droplets in the other direction, I have to go as a random walk. So I have to create to enlarge the droplet and then make it smaller and so on and so forth. There was a question because I heard some.
Cristina, yes. I have a question. So at some point could you remember what the physicists predicted for this model? Because they were, I remember you said that they were losing a factor of 2 somewhere.
Yes, no, it was not for this model. So actually, it was even for the East model in 1 dimension. They were losing a factor of 2, but even in the constant, that was a finer thing. So for the East model in Y dimension, where the behavior is log q square divided 2 log 2, it's not it belongs to the class of the supercritical models that have a green semicircle. So in this case, the droplets are the single empty sites, and there is this factor 2 here, which was missing in their understanding, and which comes from the fact that when you have to overcome this logarithmic energy barrier, you have many ways to go through this bottleneck, let's say. So you have you have this bottleneck, which is which corresponds to the fact that you have to create these log Q sites, log base 2. So you have to, if you want to go to the distance 2 to the n, which is here for us Q, you have to create n empty sites. But here, what they were missing was the correction here. So in this case, it won't. If the question is, will this correction that we find for East with this finer understanding of the entropy correct something here? No, it won't correct the exponent. It will correct just the constant in front. And furthermore, for these cases, we don't have this finer understanding of the entropy. So in order to pick the right constant, so there is not even for the bootstrap, there is not the right constant in front of the logarithm for the models. It's just the right number of exponent here in the logarithm, but not the constant in front. So having the right constant is something more subtle.
Thank you.
Okay. So some ideas on the tools, on the obstacles before giving the ideas on the tools. So for critical models, these droplets, I said that they are mobile in a typical environment. So the environment around, if I want to move, say, the column for the Duarte model on the right, it will have to be inside an environment in which at each step I'm finding at least one empty side in the next column. And this environment, so the difficulty is that, as I told you in the first lesson, I cannot allow myself to, say, freeze this environment to a good configuration. So a configuration which allows my column to move because it contains all these empty sides. I cannot use these types of tools. So I have to deal with an environment around my droplet that is changing all the time and can lose its goodness. So it can lose this single empty site, which allows my motion. And furthermore, also, in fact, also these droplets are not some rigid objects. In fact, these droplets can say the column of length at least 1/q log q for Duarte. If I define the droplet in this rigid way, this droplet can disappear because in the middle, I have one single site in which the constraint is satisfied, and that site can be occupied. So I cannot allow myself to have some so rigid definition. This is at variance with the case for the FA1F, as Milton was asking yesterday. For FA1F, since I have a single, so I have a single empty site, so at least I know that at the end, one single empty site will remain. Here I can, if I use a too rigid definition of droplets, I don't even have them. I can destroy them during my dynamics. So, and furthermore, as we see, as we just saw, the last observation here is that since the motion is very involved, it's very difficult to use for this to study these dynamics sort of the canonical path arguments type of arguments. So what we have to do, and I'm just mentioning the tool briefly because I will we saw them better in the case of the FA2F model, is to, in order to obtain, so in order to obtain upper bounds on the time scale, the first tool that we use is to establish what I call here a long-range Poincaré inequality. A Poincaré inequality is simply an equality between the variance and the Dirichlet form. So establishing the relaxation time for a certain model. Which model? It is a model with long-range constraints, which is a key tool for our study, because it's the tool that allows us to freeze the environment. So the environment cannot be frozen in the sense that I cannot compare two dynamics in which compares them in the sense that they stay ordered in some sense. If I let one dynamics evolve normally and in the other one I freeze the environment. But at the level of the Dirichlet form, so at the level of the study of the spectral gap, what I can do is that I can look at an auxiliary dynamics in which each region of the system can be updated only if, say for example for the Duarte model, say that I'm looking at some regions which are of the size of the columns. Let me make some loose arguments here to tell you what is this. Say that I'm looking at regions which are of size 1 over q times log corrections here. Okay, what we can do is to first establish that if I take a dynamics, an auxiliary dynamics, like the one that we were defining to study the spectral gap of the East model, but now a dynamics which is on a renormalized lattice, so I take my two-dimensional lattice and I renormalize it into boxes of the size of the droplet. See that we are considering the East model, the Duarte model, so the size of the boxes will be 1 over q. Okay, so first of all, I renormalize on that size. Okay, then the first dynamics that we study, instead of studying directly the Duarte dynamics, is to consider a dynamics in which on each of these blocks, so these renormalized blocks, I have a clock. When the clock rings, I try to update the configuration of the block. I try because, as usual, I'm putting a constraint in order for that update to occur. And the constraint here is something that asks for that block, suppose that I'm ringing on this block, it asks for this block to belong to a long path of blocks, with a different color perhaps, to the long path of blocks, this one, etc., this one, which are all good in the sense that they contain a sufficient number of empty sites on each line, in this case 1, in order to make my column be able, or my region to be able to move inside that cluster. Okay. So the first point is to study these renormalized dynamics, which at first sight has nothing to do with our real dynamics, but which allows us to see that to obtain a key inequality, which looks more or less of this form. So the variance of the function over the whole, any function over the whole volume is smaller than the sum over all these boxes. Say this is the box Bx, etc. I'm making a sum over all the boxes of the variance over the box, because I'm making a dynamics which is updating just the configuration on the box, multiplied by a constraint. Okay, and this constraint is the presence of this long path, which is good in the sense that on that path I'm able to move my droplet. Okay, and okay, I will also have to ask that on this long path somewhere there is one droplet in order that I can move the droplet inside the path. Once I do that, and this is okay, you can consider that as a separate argument, say it's an analytic argument with which one can prove that provided the length of the path is chosen sufficiently long and the size of the box is sufficiently large so that the probability for each box to be good, to allow the droplet to go in is sufficiently large, then this this dynamic simply has a finite relaxation time. So this auxiliary dynamics has a relaxation time here in front, which is simply finite. So this looks like what we were doing for the East model. So we are, but it's not the same. But the spirit is the same. We are not doing a sort of a bisection procedure, but we are doing a renormalization. So we take the complete dynamics, the complete, sorry, the mean over the entire measure, so on the entire volume. And we, by studying these auxiliary dynamics, we can decompose these variance, upper bound these variance as the sum of local variances, locals on the block boxes. But look now, what I have gained is that I have in front of each block, this constraint, which is telling me, which is pretty much as the constraint that I was gaining in front of the first block when I was doing the bisection for the East model. This constraint is telling me, now you are guaranteed that starting from this box here, you have a path of boxes, which is such that each of these boxes has the good environment, the environment which will be able to let my droplet to move in. And somewhere along this path, it's also contained in this constraint, because I'm choosing this path to be sufficiently long with respect to the goodness of each box so that this is, with respect to the size of the box, so that this is satisfied. Somewhere in this path, I also have one such droplet. Okay, so you have to imagine this little sentence wanted to say that the first point is to start from this decomposition. So I have this renormalization and this decomposition, which allows me to deal with the variances over boxes now with this good path around. And then you might think that having this long path of good boxes, good in the sense that they make this droplet move inside, I could try to do a path argument to reconstruct each single variance inside the box via exchanges which are allowed by my dynamics, because the presence of this path here tells me that I have somewhere a droplet that is able, via moves that are allowed by my dynamics, to move all over this path and reach my original box and make empty everything, then refill it by irreversibility, etc. So in principle, one should be able to use some path arguments to deal with this last part, but it's not what we are doing. More on it later, because you see that as I explained, the motion of these droplets, depending on the models, can be very involved. So involves these East-like paths and composition of these East-like paths, and it's very hard to try to deal with it with just a path argument. So identifying the motion of the droplet on the path. Okay, so this was for an idea on the tools, and this was for the upper bound on the time scales. And what about the lower bound? So what is the key? What are the key tools to construct lower bounds? So first of all, there are the classes for which the lower bound are just immediate for us. We don't have to work because they are provided by the bootstrap results. Because for all the models, like the unrooted models or the finitely critical models for which the behavior has the same scaling as for the bootstrap, we already saw yesterday that the time scale of the stochastic dynamics is lower bounded by the one of the bootstrap, because the bootstrap does the best that it can in order to empty everything. So in that case, we don't have any work to do. The work has to be done in the case as for the Duarte model, in which the scaling for the stochastic dynamics is much big. So the divergence for the stochastic dynamics is much bigger because we have this double exponent. And the idea is, as much as for so driven by the ideas for the East dynamics, so the idea is to try to construct a bottleneck that is our dynamics has to overcome to go and infect the origin, which will involve a logarithmic number of droplets. So, but as I said before, I won't explain this here, but just a warning. We will not at all be able to work with these making combinatorial arguments using rigid objects like empty columns, because all these objects, if I take them to rigid, they don't have an oriented motion. They simply can disappear by verifying the constraint. So one has to be very careful in this construction. Okay. So I think that perhaps if there are questions, the best is to start at this point, to stop, sorry, at this point, because I see that it's 24.
Okay. Thank you very much. Any questions? Okay, if there are no more questions, let's thank Cristina for a very interesting lecture.